where we ran out of time last time, we were on tautologies and contradictions. Okay. A tautology, oh, I missed one, okay, or two. A tautology is a statement that is always true, regardless of the truth values of the individual statement substituted for its statement variables. A statement in this form is called a tautological statement. A contradiction is a statement form that is always false, regardless of the values of the individual statement substituted for its statement variables. A statement in this form is a contradictory statement. All right, so some let's see, it's not loading properly. Show that the statement of the form P or not P, the slide got screwed up, is so it's kind of hard to see, but P or not P is a tautology, and P and not P is a contradiction. Yeah, it's the slide's kind of screwed up, so but you do this by doing a truth table with your your statements, and a tautology has all truths in the final result. A contradiction has all falses in the final result. So P or not P is always true. It's like saying it's sunny outside or it's not sunny outside. It's going to be one or the other. So it's always going to be true. P and not P is like saying it's sunny outside and it's not sunny outside, which doesn't make sense. It's a contradiction. It's just plain false. So regardless of the circumstances, P and not P is false. If T is a tautology and C is a contradiction, P and T is equivalent to P. P and C is always false, is a contradiction. And with a true value, which is a tautology, is going to be the original value. And anding a value with a false statement is always going to be false. So that's always a contradiction. Yes? Yes, think of the up arrow as an A without a cross in it for and. That's how I remember it. And or is the opposite, the down arrow. So you can see here from the truth tables, that P and T is the same. It has the same resulting truth values as just plain P.
All right, another question. When it comes to the or situation, I know it's not represented on right now.
Yeah.
When it comes to the or situation, like the second option, the one on the right, the or.
Okay.
Like, if you go back to the other slide where it was showing. Okay, so when it says or here.
Yeah, where it says or here, It's P or not P. Yeah, or is in the middle. It's yeah. But anyway, you can see here that P and C is always going to be false. So it is a contradiction as well. All right, summary of logical equivalences. These laws are the laws used for manipulating logic. These are the same laws that you have in digital logic. If you've taken that, I forget. Show of hands, who has not taken digital logic yet? Okay, so a few of you. Well, this will give you a little jump on that. Uses slightly different symbology, but commutative law, P and Q, is the same as Q and P. Associative law with ands works as well. The associative law that you recognize from algebra. The distributive law is a little bit kind of screwy with logic. P and the quantity Q or R is the same as P and Q or P and R. It distributes just fine, but it also kind of similar to the algebraic version, but it also works the other way when you reverse the operation. P or quantity Q and R is equivalent to Q or P or Q and P or R. So, identity laws. P and a tautology is equivalent to just plain P. P or a contradiction is just plain P. It can just be dropped off. The tautologies and contradictions can just be dropped out of the expression. All right. Double negative law we went over last time with not P is the equivalent of P. Universal bound laws. P or T is a tautology. P and C is a contradiction. De Morgan's law. You invert it. An inversion of a operation. You change the operation and invert the statements. So the not of the quantity P and Q is the equivalent of not P or not Q. You invert and change the operation. And it works both ways with and or being the operation to begin with. Absorption law is a little bit hard to follow. I'm going to leave that to you to demonstrate the equivalence and all that sort of stuff in your notes. And then finally, the negation of T and C. Obviously, opposite of true is false. The opposite of false is true. So opposite of a tautology is a contradiction. Opposite of a contradiction is a tautology. All right. So, using these laws, verify the logical equivalent of that expression. So, you manipulate the expressions like you would in algebra, using the same laws, just in slightly different ways in some cases. So, De Morgan's law, to split up, to take care of an inversion. Double negative law eliminates eliminates these negations. And then the distributive law, because you have P and P here, you could distribute that out. Come on. And leave P or not Q and Q. And of course, not Q and Q is a contradiction. So you put P or contradiction, and the identity law, P or a contradiction is P. So you can reduce logical expressions by using these manipulations. Like I said, similar in nature to the algebraic laws for reducing equations in algebra. So, and that is it for this slide. One thing I was wanting to show you on Tuesday, but the big blue button function on Canvas doesn't have a whiteboard option, so I had to wait for today. In here, in math classes, not is with the squiggly line. In a logic class, in the philosophy department, it's this sign. In digital logic, it is, I'll do it with a variable, A prime or A bar. Okay? And then you have C++, where you have the exclamation point. It all means the same thing. Everybody likes to have their own little lexicon of symbols and all that sort of thing. In math, A is the up arrow in math classes. If you take abstract math in the math department, basically takes the concepts from this class and takes it a few steps further. Fun class, actually. I took it when I was an undergrad. In logic class in the philosophy department, it's an upside down U. In digital logic, it is a star or a dot, like multiplication. And if you look at the binary of the AND operation, it does resemble multiplication mathematically. 0 times 0 is 0. 0 times 1 is 0. 1 times 0 is 0. And 1 times 1 is 1. That's the AND operator. In C++, it is the double AND symbol, right? Am I remembering that correctly? The double AND symbol in if statements for Boolean operations. And then the OR statement, or the OR operation, is the down arrow in math. In logic, it's a U for union, because if a element is in one, the elements of one set ORed with the other with another set, it is the union of those two sets. So that's how you remember that the U is the OR operation in a philosophy logic class. In digital logic, it is the plus sign. In C++, it's the double bar, if I'm recalling correctly. I'm not a big C++ person, but I believe that is correct, isn't it? I'm sorry? Yeah, it's an OR. Yeah. So the symbols you run into depend on who you're talking to. Talking to a philosophy person, you run into this row. Run into a mathematician, they're going to use these. An electrical engineer is going to use these. And a computer programmer will use these. So it just depends on who you're talking to. So get familiar with the various symbols for logic. The rules are all the same. How the commutative law, the associative law, identity law, De Morgan's theorems, all those are the same in digital logic, in math logic, in philosophical logic. All works the same. So it's just a matter of different symbols. Sure. The only set that I've been able to find in that you could use for like typing up a document where the symbols are in Microsoft Word and all that sort of thing are this set and that and those three. These other ones, you may or may not be able to find them in Microsoft Word when you're typing up a homework or something. So if there's an assignment where you have to do it, typing and all that sort of stuff, and you use one of these symbols down here, I'll accept it. If you can't find the symbols up here on the top row. Although this one is on the keyboard and this one is on the keyboard, this one you might not be able to find. I haven't been able to find it yet. So, yeah.
It's on Google Docs.
It is on, all of them are on Google Docs? Okay. So you can do it that way.
It all already was on. And the bottom is where it's on.
Oh, okay. Okay. Well, I've just been using Microsoft Word and I've been having a hard time with it. So, but anyway, all right. Anybody else need this up there? Need this up there anymore? No. Got to take a quick picture. All right. I guess get from the people's wrestling. It's about time to head out. So Have a good day. We'll pick up on section 2 of chapter 2 on Thursday. Have a good afternoon. Oh, Tuesday. I'm sorry. Today is Thursday.